Furthermore, there's some other things. One of the things that you'll sometimes find people talking about, as in movies like What the Bleep, into which poor Marlene Matlin got sort of pulled in as the haunted star of the movie. He was somehow cured by quantum entanglement. Well, quantum entanglement is actually a very fragile kind of thing. So suppose that A and B are two electrons and they're entangled. Well, then it's really hard to preserve that entanglement. You've got to keep them both isolated from the surrounding environment. As soon as A interacts with this environment with all these air particles and all these molecules and zillions of things in it, what happens is this very tight entanglement that they started out with that gave us these nifty EPR correlations, it just kind of dissipates, just sort of withers away, so that it becomes, for all practical purposes, zero. Okay, it just isn't there anymore. This goes along with a phenomenon called decoherence, for any of you who have your very word, but nonetheless, the point is, quantum entanglement is fragile. And once again, this comes from the bottom level of quantum theory. But as soon as you get systems that are in a noisy environment, and noisy just means lots of stuff like dust particles, objects, and so on, and you start interacting with them, the tight entanglement gets spread out, dissipated through that environment, and then these correlations just disappear. Furthermore, I remember once having a conversation with a gentleman, who was very interested in these quantum phenomena, and he kind of, I think, wanted the world to be a certain way. Maybe many of us do. And so we had this conversation, and we talked about quantum mechanics and many things. And he said, well, don't you feel that as a result of this intense conversation we've had, that our brains are now entangled? Well, the answer is no. And the answer is no, not because I didn't find this gentleman a perfectly agreeable person to talk to, or wouldn't invite him to a cocktail party or anything like that. That's not the point. The point is that his brain and my brain are in the middle of an environment that is incredibly thermodynamically noisy, and quantum mechanics would say, nope, the entanglement would just, any entanglement that could possibly have been, would just dissipate essentially into nothing. So our brains, for all practical purposes, couldn't get entangled in that way. So where does this leave us? This is where we'll finish. Well, these entanglement phenomena are pretty central to quantum mechanics. Schrödinger said that they were the central to human theory. And entanglement is wonderfully weird. There are all kinds of neat things about entanglement. But not that weird. So, I know I've gone over a bunch of stuff here, and I think the best thing to do now is to stop, and we can talk about it. If you have questions or things you want to raise, we can do that. Sir?
Maybe this is a bad analogy, but could these particles be acting like rubber bands, so to speak, to explain entanglement, that entangled in a particle, like say, when they sort of stretch out in waves, and when they hit measurements, they sort of revert to particles again? Sort of like
there are views like that. The view that you're suggesting is one that some people would describe in a different way. They'd say that one view would say there are particles like electrons and so forth. And then there's this mysterious thing. I don't want to put too much stress on the word mysterious here. This complicated thing called the wave function. And that's a very important idea in quantum mechanics. And some people would say, well, the wave function really is a kind of a real thing. It's kind of like a field in its own way, only much more complicated. And so there's this wave function that connects these two particles, but it's not like a classical electromagnetic field in a whole bunch of ways. And so what they would say is that, yeah, sometimes you've got this sort of spread out wave that sort of collapses. And that's one view that some people have about what's going on here. It's one view among others. So that could be, but whether it really is, hard to say.
just follow up, could you say that maybe speeds are instantaneous within the wave function?
What this view in its usual form says is that there is a particular frame of reference in which the speed really is instantaneous, and that special frame of reference has a special role to play in nature, but for various reasons, it's not accessible to us which frame of reference that is. And this is a serious and interesting view that has led to serious and interesting physics, but we're not at the point now where we can test it experimentally. Some people hope we will be, but the experiments will be really hard. Sir?
You talked about, if I didn't misunderstand, you talked about the prohibitions for remote communications.
Yes.
Could you just relate that to, there are some experiments going on in
Yes.
remote communications. Could you talk about some of those in light of that prohibition?
Okay, there are some very interesting phenomena here that I'll try to kind of allude to. There's sort of a trick to it. There's a whole branch of the foundations of quantum mechanics that's concerned with things like quantum cryptography and so on, where you can somehow use quantum means to make communication between two distant people more secure and so on. And so quantum information is a fascinating subject that has some role to play, but briefly what makes it tricky is this. Suppose you and I have this shared entangled particle, and we're going to use this in some sort of way to sort of enable us to facilitate certain kinds of communication. It still turns out that the only way that we can do the full trick is that I actually do have to call you up and give you a bit of information. In other words, what happens is I can get a little bit more information to you by combining a classical channel, like a telephone, with quantum entanglement than you would expect classically. But in order for it to work, we have to have the good old-fashioned classical communication. And so it's not a case of merely quantum means allowing me to communicate with you. In all of these quantum communication protocols, there is a classical element of me giving you the old-fashioned way some information.
Is this more than the key management problem?
The key management problem is related to it. Yeah,
it's more than, but it's more than, in other words, there's more involved in that. The dependency on the classical channel.
Well, I don't know whether it's more or less involved, but the bottom line is that it's always going to be necessary in these cases for you to get any useful information from me, that part of that information comes through a classical channel. And once we combine the classical and quantum, you still get some very interesting things going on that you wouldn't get classically. But in order to do it, you've got to have the classical piece.
Thank you.
Sir, yes.
But no extrapolation of theory is required to use quantum phenomena, at least theoretically, for simple cryptography, right? Because cryptography simply requires that you and I have a parallel process to perform, even if we don't know what it is exactly.
Right.
And the quantum mechanics doesn't forbid that, right? It doesn't.
No, it doesn't. It doesn't. No. And the hope is that because of some of the features of the quantum state, you'll be able to do things like decode encrypted messages more efficiently. That's one thing that quantum computation might allow us to do. It might have these factoring algorithms that would allow a speed up that the classical computer wouldn't. This is all a field that is very much emerging now, and we're still scrambling to figure out what's what. I say we, as though I actually have the details. I don't. And there's also questions about whether you can use quantum mechanics as a way of detecting eavesdropping along the communication channel. And there's all kinds of fascinating things about that sort of thing. But once again, just to reiterate the point I made to this gentleman, whenever it's a case of me getting stuff to you, there's always going to be some classical element involved, even if it's marching a particle over to you or something like that.
Right, but the sharing of keys isn't an information transfer, and so it doesn't
Right.
necessarily
That's
fall
right.
into
That's right. That's right. And then in that case, as I said, the quantum thing might be efficient ways of decoding by fractoring large prime numbers. Yeah, not fractoring large prime numbers. Prime factoring large numbers. Yes.